Okay, so in this video, I want to clarify on one of the problems that I presented. So let's actually go over that right now. So it referred to this example. Uh, let's see. Okay, here we go. So it referred to this example. So we want to figure out the integrating factor and then solve this equation here. The integrating factor in this case will look something like this. So in your problem set, they give you an integrating factor like this, and you want to try to multiply both sides by mu in this equation here. And you'll get that you'll get that x to the m times y to the n times 12 plus 5xy plus x to the m times y to the n is 1 plus 3x squared. dy is 0. Right? And so we'll have 12xmyn plus 5 plus 1 y to the n plus 1 plus 6 times, it 6 raised to the n plus 1, and then we'll have a y raised to the n minus 1 power plus 3 times x to the n plus 2 times y to the n. This is dy, and this here is dx. This has to equal 0. Right, and then we want to use this differential equation to solve for exactness here, right? And so if we use this quantity as m and this here as n, right? Partial of m with respect to x, this equals, I'm sorry, partial of m with respect to y. I got to get this right. So partial of m with respect to y, this is 12 times n. That's the m, y to the n minus 1. And then plus 5 times n plus 1. It's the m plus 1 times y to the n power. Okay, and then the partial of n with respect to x, that has to equal to 6 times n plus 1 times, ooh, I'm sorry, that's not right. That's not right. So that's 6 times n plus 1 times that's the m y to the n minus 1 plus 3 times n plus 2. Let's raise the n plus 1 times y to the n power. And so in order for a differential equation to be exact, these have to equal, right? Partial of m with respect to y has to equal to the partial of n with respect to x, right? And so what that means is, okay, these two functions have to equal, right? But notice, right, this is kind of special because we have these terms as the same. I don't know if you noticed that, but these are the same. So all you got to do is just make sure that, God, you have to make sure the quantities are, the coefficients are the same, right? So what that means is, so by the coefficients, so match the coefficients with x to the m, y to the n minus 1 terms. So that means 12n has to equal to 6 times the quantity n plus 1. And then match with the coefficients attached with x to the n plus 1 times y to the n. So in that case, it means 5 times n plus 1 equals to 3 times n plus 2. N plus 2. Okay? So all we got to do is solve for n and then m here. All right? Okay? And so we'll have 12n equals to 6n plus 6. And then 5n plus 5 equals to 3m plus 5. I'm sorry, 6. Right? And so 12n minus 6m is 6. 5n minus 3m equals 1. Okay, and then so this would reduce down to these equations. So the first equations is divide by 6. Okay. Right, and then I multiply by the first equation by 3, so I'll have 6n minus 3m equals 3, and then 5m minus 3m equals 1. And if I subtract the equations, I'll have n equals 2. And what that means is if n equals 2, then so 4. And then m is 3. Okay? So your integrating factor, right, is x cubed y squared. That would make that equation exact. Okay. And yeah, so so that would make it exact. Okay. And if that is true, so n is 2, so that would be 12 times 2 is 24. X cubed, n is 2, so that's y plus 5 times. So I'm going to double check my answer. Okay. Yeah, so 5 times 3, that's 15. So that's 15. That's to the 4th y squared. And that should be the same. So 6 times 3 plus 4, that's 24. 24 x cubed times y. Y was 2. 3 times 5, that's 15. That looks good. That's the 4th y squared. So yes, I do get the same function. Nice. Great. All right. So now from here, all you have to do is just take, that's the hard part. Okay. So that's the hard part. So all we have to do, excuse me. So all we have to do now is take, can I erase this? So all I have to do is just use the method to solve for the general solution by using either this function or the other one to solve for a general solution. Okay. So yeah, you're just multiplying both sides by that integrating factor, making it exact, and then using that to solve the differential equation, right? And so yeah, so this is the redefined version of the differential equation. So really, so there's a general solution for which partial of f with respect to x is equal to, so all right, I gotta be careful here. So it'll be 12. The m is 3, y is 2. So I squared plus 5x, x is 3, so x to the 4th, y and plus 1, 3. And then partial of f with respect to y, that's 6x to the 4th, y. So m minus 1, so that's y plus 3 times 3 plus 2, which is 5. The n is 2, so that's y squared. Okay. So so from here, you're going to solve that a general solution f is equal to the integral of f of x dx, right, plus a constant, right? Okay. So integrate that function. So with respect to x, so it would be 3x to the 4th, y squared. So that will be plus x to the 5th, y cubed, plus h of y. So that's your function f. And then take the derivative of that function with respect to y. So that would be 6x to the 4th, y cubed, plus 3x to the 5th, y squared, plus h prime of y, which equals to 6x to the 4th times y times y. Hold on a second. That should be y. Okay, yeah. All right, that's a y. And y squared. Okay. All right, cool. Cool. I'm on the right track. So that would be times y, and so those will equal. These terms will cancel. You'll just get the h prime of y is 0. So that means h of y is just a constant, right? And so what that means is that your function, right? So your function will equal to, well, 3x to the 4th, y squared, plus x to the 5th, y cubed, and that has to equal to a constant. So that's your general solution. Okay. Hopefully that clears things up, and I hope that made sense. Okay, so here are some problems for you to work with if I haven't gone over that slide many times. So this deals with exact equations, and this is some problems that deal with special integrating factors, right? Okay, But that's basically it for linear differential equation. I'm sorry, that's it for first order differential equations. Um, so for the next set of videos, we're going to be looking at different models of first order differential equations. This is the most exciting part. So we're going to get into models that look at a stirred tank, right? We'll look at population models. We'll look at Newtonian mechanics. Newtonian mechanics, right? Um, like Newton's law of cooling and stuff like that. So, um, and and I'm trying to think, and then we'll use different algorithms like Euler's approximation, and I'll talk about another method for finding a solution curves called the Runge-Kutta method, right? So, pretty exciting content in the next videos, right? So, hope this helped. If you have questions, just let me know. But otherwise, thank you for watching this other part, and I'll see you next time.